inclusive reporting, and I'll be going through what a control system is, what stability is, and a method we can use to check stability in a control system. So we ask, what is a control system? Okay, so a control system is a system that manages or regulates the behavior of other systems or devices towards achieve the desired output. For example, in a car, the cruise control system, it helps maintain a constant speed without the driver constantly adjusting the accelerator. Okay, yeah. When what is stability? Okay, stability is a very important tool in control system because it behaves to ensure that the system doesn't go out of control. For example, let's say if you're flying a drone and it's unstable, it would crash instead of flying smoothly. So one method of checking stability or to use stability properly is the Routh Criterion. It's a mathematical technique that helps engineers to determine whether a system will be stable or unstable without needing to solve a complex equation.
So in this video, we are presenting using the equation s to the power 4 plus 20s cubed plus 15s squared plus 2s plus k equals to 0. Our goal is to determine two things. First, the range of values of k that make the system stable. Second, the condition for marginally stability. And third, the frequency of oscillation when the system is marginally stable.
I'm going to talk about the concept of the Routh table. To solve this, we use the RH method. The RH criterion is a rule used in control systems to determine whether the system is stable or unstable without actually solving the characteristic equation. This method allows us to check the stability without solving the equation directly. Instead, we construct something called the Routh table, and by analyzing the values in that table, we can determine whether the system is stable or not. Thank you.
In this part, I'll be constructing the Routh table from the characteristic equation. The characteristic equation is S4 plus 20S3 plus 15S2 plus 21S1 plus K is equal to 0. Now, the first two rows can be obtained from the characteristic equation. The first row, we are going to fill it with the even powers, S4, S2, and S0. So the first row will be 1, 15, and K. Then the second row will be odd powers. That's going to be 20, 2, and 0. For the S2 rows and the S1 rows, we are going to use determinants from the rows above. So for the S2 row, A is going to be 20 times 15 minus 1 times 2 over 20. We are going to get 14.9. For B, 20 times K minus 1 times 0 over 20. Then we are going to get K. So the S2 row is going to be 14.9 and K. We are going to do the same determinant way for S1. We get 14.9 times 2 minus 20 times K over 14.9. Then, so the S1 row is going to be 29.8 minus 20K over 14.9. Then the S0 row is just the constant, which is K. Thank you.
Okay, so now we calculate the S squared. To find the first value, we use 20 times 15 minus 1 times 2 divided by 20. This gives us 300 minus 2, all divided by 20, which is equal to 298 divided by 20, giving us 14.9. So for the next value, we also use 20 times k minus 1 times 0, all divided by 20. This gives us 20k divided by 20, which is equal to k. The S squared row becomes 14.9 k.
So now we are going to determine when the system is stable. From the Routh table we constructed earlier, we are going to use a very important condition for the system to be stable, and that's all the elements in the first column must be positive. That they have to be greater than 0. So we look at the first column for our table. From there we get two conditions: k must be greater than 0 and also 29.8 minus 20k must be greater than 0. Now when we consider the second inequality, we are going to get k to be less than 1.49. So combining both equations, we are also going to get 0 to be less than k, and that's also less than 1.49. And this means that our system is stable within the range of k. Now to check what happens at the boundary, we are going to let k to be equal to 1.49. And at this point, the system becomes what we call marginally stable. This means the system will start to oscillate continuously. And then from there, you can find the frequency of this oscillation by forming an auxiliary equation from the rule above, which gives 14.9s squared plus 1.49 to be equal to 0. Now when we solve this, we are going to get s squared to be equal to negative 0.1. Taking the square root of that gives us plus or minus j 0.316. Since these roots are imaginary, the system will oscillate. So the frequency of oscillation is going to be 0.316 radians per second. And this is how we determine both the stability range and then the system behavior at marginal stability.
When k equals 1.49, the system becomes marginally stable. At this point, we form the auxiliary equation from the row above. 14.9 is squared plus 1.49 is equal to 0. Solving this, s squared will become negative 0.1. So s is equal to plus or minus j 0.316. This means the system oscillates. The frequency of the oscillation is 0.316 radians per second. Thank you.
Okay, so in conclusion, we found out that for the system to be stable, the range of values of k is when k is greater than 0 but less than 1.49. And also, the system is marginally stable when k is equal to 1.49. We were also able to find out that the oscillation frequency is 0.316 radians per second, and this whole concept of stability has a lot of applications in fields like robotics and stuff.